What is up, guys? Welcome to 3.6 directional derivatives and the gradient vector. Now 3.6 will be split into two sections, so I'm actually going to make 3.7 the gradient vector only, and 3.6 is just an intro to the gradient vector and directional derivatives, so because this is a very long lesson. So first of all, recall that we have f sub x and f sub y, right? Both f sub x and f sub y describe derivatives in the x direction and the y direction. So describe the tangent lines of a point on a surface in the x direction and a tangent line on a y direction bounded by a plane, right? Like I did describe in 3.3. So that's f sub x and f sub y. Now, at a point, you can you can go this way and you can go this way, right? Look at the bottom, you can go this way and you can go this way, which will produce tangent lines of respectively this and this, right? But obviously that's not the only ways. Those are not the only ways for you to do a tangent line, right? For you to do tangent lines, you can take it in any direction you want, right? And you're not bounded by what direction you take. So what if we did take it in a different direction of a unit vector? I'll explain why it has to be a unit vector in a second. But how will this affect the derivative? How will this affect the derivative? Now, if you see a tangent plane, and I'm gonna go move it right here, move to this slide right here. If you see a tangent plane like this, sometimes the normal vector to that tangent plane isn't like a totally x normal vector or a y normal. The normal vector doesn't have a component of 0 in the x or 0 in the y, so it depends on both x and y. So you could say that the slope of this plane depends on both x and y, and there is a path you can walk on this plane. There is a direction that you can go on this plane that will give you a direction of 0, and there is a direction that you can go on this plane that will give you the direction of fastest increase, and there's a direction that will give you the direction of least increase. In this case, it probably will be like that, and if you walk on this line right here, you will probably not increase your z value. So that is what the differential is for. The differential is for calculating a change in f, a small change in f is equal to, when you walk on the tangent plane in the x direction, times f sub x, which is denoted like this. So you move up, or this is the y direction first. So in the x direction, it will be something like this, f sub x. You move up the tangent plane, probably like right here. So there's still a little bit difference, but as we move closer and closer, it will be better and better. And then you move up in the y direction like this, right? So that's how you move on the tangent plane for you to get to the point, right? The approximation is f sub x, you move in the x direction, times dx, plus f sub y, you move on the y direction, times dy. So that's kind of what we want to do this time. However, there's something that we have to take into account. F sub x is an entire change in x, right? But when we take partial derivatives, we only want for every one change in x, how much does z change, right? So for every one change in x, how much does f change, or how much does z change, right? So I can also write dz is equal to f sub x dx plus f sub y dy. So if we change, okay, this is z minus z0, right? Or, well, z minus z0, so z minus the original z that you have is equal to the derivative plus this. So if we don't change y at all, let's say dy is 0 and dx, or change in x, is 1, we'll have z minus z0 is equal to f sub x. So that is right there the definition of the partial derivative, right? or not the definition of the partial derivative, but how you can get the partial derivative from the differential. So when you change x by 1 and you don't change y at all, you get a new z. You'll change z by an amount delta z. You will change z by an amount delta z. Or I guess I should say dz, not delta z, I'm sorry, because it's a differential. So dz is how much you will change. If you change x by 1 unit exactly, you will change dz. If you change, let's say, if you change y by 1 unit exactly, you will get f sub y, right? dx equals 0, dy equals 1. You will get the change in z equals f sub y, right? So that's what we want for our derivative. We want the change to be purely due to the direction and not the magnitude. We want the change to be purely due to the direction and not the magnitude. So we fix dx, we fix the changes to be 1 only. So the magnitude is always 1. It's kind of like when I said the unit vector, the projection, right? The unit vector is pretty much direction. It dictates your direction, because when you multiply anything, or when you do a dot product or cross product with it, it's not going to change the magnitude. It's just going to change your direction, so or your component for the dot product. So that is why what we want is a unit vector, because we only want to change the direction. We only want to see how much the z coordinate changes based on the direction, not the magnitude. If we had something like dx equals 1 and dy equals 1, if we had dx equals 1 and dy equals 1, we'll have dz equals f sub x plus f sub y, which is more a combination of the two derivatives, which is, I mean, yeah, it is a directional derivative, but the magnitude, the amount that you had to travel to do that derivative, is change in x 1, change in y 1. So if you do the Pythagorean theorem, you will get a change in square root of 2. That's not what you want. You only want a change. You only want for every one movement, how much do you change in z, right? That's the idea of a slope. The slope is, or the slope in 2D is y equals mx, right? It's y equals, for every change in the x direction, how much are you changing in the y direction? So m is the change in y over the change in x times x, right? So for every change in the y direction, for every change in the x direction, let's say it's 1, how much are you changing in the y direction? And we do the rise over run stuff, but eventually, let's say we rise 8 every 4, every single time we move 4. Eventually, we are going to have to simplify that into 2 over 1. So every 2 change in y you will get, or every 1 change in x you do, you will have a 2 change in y. So it's the same thing for this one. Every 1 change in x you will get an f of x, or f sub x change in y, or change in z, I'm sorry, f sub x change in z. Every 1 change in y you get an f sub y change in z, right? So every 1 change in this particular direction, you get what combination of f sub x and f sub y will you get, is what we want to answer today. So that's how you get every derivative. I just explained it. You have to take a unit vector in some direction, and you have to combine it with f sub x and f sub y in order to get a particular directional derivative. So it kind of goes like this, right? So if you have a unit vector like this is in the x direction, this is in the y direction, but we want this. So how are we going to get this? The answer lies in the angle in between the x and the y axis. Specifically, this vector, let's say this vector is we're gonna call it this, or no, I'm sorry, we're gonna call it d u. So it's u. This is the unit vector. We want to find this this change right here, or as we move in this direction, how much it changes, right? And we want to take the x and the y component, and we want to in this case it's 1/2 square root of 3 over 2. We want to take the x and the y component, enough of the x and enough of the y component to make the total change a magnitude of 1, so we can examine only the change in z due to direction and not magnitude. Okay, so du, right, and in this case it's the unit vector. The u is in the direction of 1/2 and square root of 3 over 2, and this is just a point, so x, y, right? So this is how you would write the function, and let's say this is a function f. So d with the unit vector at the bottom, I think I have notation somewhere, and then of the function, right? So because we gotta pick a point, and then we gotta pick the direction that we want to go as well, right? In this case it's 1/2 square root of 3 over 2, and the directional derivative, the direction, how you're going to be able to find that unit vector, depends on the angle between the x-axis and the direction that you want to go to. So this is the limit definition of a directional derivative. I don't want to go through it. I really don't. Yeah, so this is the limit definition. So you could see that we're going a change in h. We're going a change in no, not a change in h. We are having a change in the x direction, and we're also having a change in the y direction. But we're changing by different amounts. We're changing by in this case an a amount, and then we're changing in this case by a b amount. And in this case, I should also specify that a comma b is a unit vector, like this. A comma b is a unit vector. You could say like u hat. But a unit vector is a comma b. It has to be a unit vector. If it's not a unit vector, you're taking more than one magnitude, so you're gonna have to divide by that magnitude later on. So in this case, I find the directional derivative example. I did not want to do this during I did not want to do this during the class, during the video, so I just did it right here. You can mesmerize on it. You can do it yourself if you want to. If you want to do it yourself, try it with x squared minus xy plus y squared, same direction. But yeah, this is how you find the directional derivative using the definition. Don't do that though, because there's a lot better way. This is your notation, right? So the derivative, the directional derivative in the direction, is root 2 over 2 root 2 over 2 of f of xy is equal to this, right? The direction of root 2 over 2 root 2 over 2 f of xy is equal to this. Now we bring back our function. If we bring back our f sub x dx, I'm just gonna make this a little smaller. If we bring back our function d f is equal to f sub x dx, this is a differential, right? You could see that our change in x is root 2 over 2. Our change in x is root 2 over 2. Our change in y is root 2 over 2. Right? We're moving the direction root 2 over 2. We're going from 0 to root 2 over 2, 0 to root 2 over 2. And then we can find 3 as our f sub x and square root 2 as our f sub y. 3 is our f sub x and square root 2, or no, not square root 2, I'm sorry. This is square root 2, so 1/2 y is our f sub y. Right? You could see that df is equal to 3 times root 2 over 2, 3 times root 2 over 2 plus, in this case, right, df is 3 times root 2 over 2 plus 1/2 y times square root 2 over 2. If we go back to this, or wait, no, is it 1/2? No, I'm sorry, it's not 1/2, it's 2. it's 2y times root 2 over 2. Right? So f sub x is 3 and f sub y is 2y. Right? And I just basically said this again, and the directional derivative in that direction is root 2 over 2 times f sub x plus root 2 over 2 times f sub y, which, if you notice, that is the unit vector dot product with this, whatever this is, all of the directional derivatives in the x direction, and the directional derivative, or no, not, well, yeah, it's technically directional derivative, but the partial derivative in the x direction, partial derivative in the y direction. So that is how you figure it out, right? You could use the angle, like what I said in the beginning, or you can dot product your unit vector with your partial vector. I will call it a partial vector. Partial vector is called something. It's called a gradient. So this is what the partial vector is. It's just a vector of partials. The gradient vector is denoted with an upside down triangle del, so del f, and it comprises all the partial derivatives. It is a vector, not a scalar. Very important for chapter 6, I think, but it's not very important right now. Chapter 5 or chapter 6, I don't remember, but it's very important for the place where we'll do vector calculus, but it's not very important right now. The gradient vector represents the direction of fastest increase at a point x, y for 2 inputs, x, y, z for 3 inputs, and like a vector x1, x2, x3, x4 for 4 inputs, and more and more inputs, etc., etc. Right, so that's what the gradient vector does. So this is how you find a directional derivative. So let's try to find the directional derivative. Find a directional derivative. F of 1, 2 if f of x, y is this, and u is this, or u is these three. So what do we want to do first? We want to find a, if you're completely clueless, we want to find the partial derivatives, right? So f sub x is equal to 1. Okay, first of all, let me simplify this. So f is equal to, I can take the 1/2 out of the power, so I get 1/2 e to the xy times natural log y. 1/2 e to the xy times natural log y. So f sub x is equal to 1/2 times e, 1/2 natural log y is a constant, and then e to the xy is, it copies itself, and then you take the derivative of xy with respect to x is y, so multiply by y. So I could just put y in here, but now f sub y is a little bit harder because you have to use the product rule. So let's do that right now. 1/2 times, I'm just going to take 1/2 out of the equation, factor it out. Leave the first, take the derivative of the second, plus take the derivative of the first. This case is x e to the xy. Leave the second. So let me get more space for myself. Okay, that might be out of the screen actually. Natural log y. There you go. So that's f sub x, f sub y. Okay, so now what do? Now we find both of these, f sub x and f sub y, at 1, 2. So we're gonna get pretty nasty numbers, is what I'm expecting. I should have made it natural log x. I'll tell you why I should have made it natural log x later. If we put 1 in the x, it's just really nice. 1/2 times natural log of 2 times, okay, so what you'll get is 1/2 times y, which is 1, natural log of 2 times e squared. F sub y is 1/2 times e squared over 2, right, because y is at the bottom, plus e squared natural log 2. I hope I did that right. I really hope I did that right. So that is your f sub y. So now what? Now we want to find a directional derivative. Let's do number 1 first. So number 1 is the directional derivative in the direction negative 1 comma 0 of f of 1 over 1 comma 2 is equal to what? Is equal to the gradient vector, which is f sub x and f sub y. So the gradient vector of f at 1 comma 2 is natural log 2 e squared, or sorry, e squared times natural log 2 comma 1/2 times e squared over 2 plus e squared times natural log 2. There you go. So the direction at negative 1 comma 0 is negative 1 comma 0 dot with your gradient vector f at 1 comma 2, which is equal to simply just the left side, negative e squared natural log of 2. And if you notice, what this direction is basically just the negative x direction. So if you're going in the positive x direction, for every one you move in the x direction, you're moving up by e squared natural log 2. That's f sub x. That's the definition. For every 1 you move in the x direction, you're moving e squared natural log 2 in the z. Or you're increasing your height by e squared natural log 2. Now if you're moving negative 1 in the x direction, then you're decreasing your height by e squared natural log 2. That makes sense, right? So let's keep going. Now we have angular bracket, 3/5, 4/5 of f of 1 comma 2 is what? Is 3/5 negative 4/5, or a negative 4/5 dot the gradient of f at 1 comma 2, which is really messy, which is going to be 3/5 times e squared natural log 2 minus 4/5 times 1/2, so 2/5 times 2/5 times e squared over 2 plus e squared natural log 2. Right? It's a very, very messy function. I honestly don't even know whether or not this is positive or negative. I think it's negative. I think it's negative in this function. 7 pi over 6 from the positive x-axis. This is a little bit tougher. It's a little bit more involved. So if you have a function like or a coordinate plane like this, 7 pi over 6 from the positive x-axis will be something like this. Right? So if we use our skills to find out what this means, we know that the unit vector can actually be directed by something called the unit circle, right? So every single time you take a point from the origin, or you take the initial point from the origin, and then you project it, or you draw an arrow to the unit circle, that's a unit vector. And how do we determine points in the unit vector? We determine them by trig. Specifically, the x-coordinate is the cosine, and the y-coordinate is the sine. So the unit vector is cosine of 7 pi over 6, sine of 7 pi over 6. What's cosine of 7 pi over 6? It's negative root 3 over 2. And what's sine of 7 pi over 6 is negative 1/2. So, oh my gosh, the door just opened by itself. So what do you get? You will get the directional derivative at, I'm just going to write u. The directional derivative at u of f of 1, 2 is equal to negative root 3 over 2 times e squared natural log 2, comma, negative 1 over 4, because 1/2 times 1/2, times, oh gosh, e squared over 2 plus e squared oh my gosh, oh, this is getting messy, e squared natural log 2. And we will make this smaller. There you go. I hope you can read that, or I'm just gonna make it look a little bit nicer so you can read that. E squared natural log 2. And that's your answer.